Hello everyone, this is lecture 21 for the quantum mechanics. In the last lecture we were discussing about the operators and mainly about the Hermitian operator. So I told you how can you check if some operator is Hermitian or not. So this should satisfy this condition that this should be equal to this. Okay, and we have discussed that the eigenvalues of Hermitian will be real and the eigenvectors for the Hermitian operator, they should be orthogonal. So we have discussed all these properties and proved that. Okay, so I gave you this homework that you need to prove that this operator I d by dx is Hermitian, means a dagger equal to a, and you need to prove that a dagger equal to d by dx, this operator is skew Hermitian, or a dagger equal to minus a. So I hope you tried to solve them. Now let me show you the proof. So as I told you, what you need to do is you need to prove this one equal to this. So first you will operate it with the cat, then you will find this result equal to this. If this came out to be this, then you can say that A is Hermitian, because this means that A dagger will be equal to A. If they are equal, then that means A dagger equal to A. So let's see if it is came out to be same or not. So first A operator, we will taking this. So it will operate on phi 2. So I dy dx, it will written as it is. So it will be phi 2x. This will be phi 1 star. Now this I will be came out of the integral. It will be phi 1 star x dy dx phi 2. Now see, this is a product of two functions and we have integration, so we can use integration by parts. So let's this is our first function, this is our second function. So integration of this means take this as it is and integrate the second function. It will give you phi 2 and put the limits minus differentiation of first function dy dx of phi 1 dagger, or the star you can write, it is the same thing. Now second integration of second function will give you phi 2. So this integration will be phi 2 because this is dy dx, it will give you phi 2 here. So we just applied the integration by part here and we get this result. I will multiply with both of them. Now see, this phi 1 and phi 2, this is some like a is inner product of phi 1 and phi 2, and we know that both are orthogonal, so this will be 0. Then we will remaining with only with this. So now you see, you can just put this minus I dy dx inside this dagger, then this minus I will become I and dy dx inside, so this will become this whole term will taken inside this phi 1 dagger, so it will be I d phi by dx dagger. Now you can see that if you take this I outside dagger, it will be minus I again and dy dx, so we can write this thing as this. Now if you say here, then this I d by dx is nothing but a, that is a, so you can write this a phi dagger phi 2, and a phi dagger phi 2 can be written in the cat and bra notation this way, a phi 2, and this is equal to means a will outside this bra operator, that will be a dagger, so this can be written in this way, and this is equal to this, or you can say that this is coming out to be this, means this is the only condition we require to prove the a dagger equal to a. So this is came out to be equal to this, means a equal to a dagger and a operator is Hermitian. So I hope you understood this thing. So let's see for the second one, that it is skew Hermitian. So we'll do the same thing with this also, and let's see what we are getting here. So let's apply. In place of I, it will be only this time. So we need to prove that this equal to this to prove it is Hermitian. So let's see, dy dx phi 2 dx. Now apply again the integration by parts. This will give you again, this is first function, this is second function, it is as it is. Integration of this will give you phi 2, put the limits, minus differentiation of this first one and integration of second one will give you phi 2 dx. Now this will give you 0 again, same way. Now see, this can be written this way now, means you can just write minus d by dx with the phi 1 star, and in the Dirac notations you can write this in this form. This is a operator, means this one a, and it is minus a phi 1 phi 2. Now see, we started with this, and this can be written, this is a, so it is written this way, and if this will go to the bra, it will become a dagger inside, so a dagger phi 1 phi 2. Now this is equal to this and this is equal to this, so means they are equal. From here you can see that a dagger should be equal to minus a, so that's how you can prove. Now let's see the equivalent form of an operator. What is the meaning of equivalent form? Means you will find a second operator which will operate on the wave function and give you the same result. Means you have some operator a that is operating on the psi, and some different operator a dash that is operating on the psi, and both are giving the same result. Then this a psi is called the equivalent of a. So I hope you understand the equivalence meaning. So a equal to this. means they both are the equivalent operator. Now let's see how can we find the equivalent operator. We have this operator A, that is dy dx x cap. We need to find the equivalent of A. So what you do, whenever wherever you will, it will be asked to you from you that find the equivalent operator, you will operate that operator on the psi wave function. So let's operate this on the wave function A psi x. So what this will give you, write this operator dy dx x cap and psi x. Now see, first this will operate on it, so it will give you, when this position operator operates, it will give you x. So x cap psi x will give you x psi x. Now the second will operate. Now this is a product rule, apply the product rule. So it will be x d psi by dx plus psi dx by dx will give you 1. Now you can take this psi again outside of this and you will get a new operator, that is x dy dx plus 1 psi. So see, this will give you same result as this operator. So this will be your new operator, which is applying on psi, and this A operator applying on the psi. So this operator and this operator are same and are the equivalent of each other. Okay. And this can be written in this form. This operator will be x cap dy dx plus this one will be written as I cap. So this is your equivalent operator with respect to A. So that's how you can find. Always operate that operator on the wave function psi x, and that's how you will get your new equivalent operator of A. So try to solve these questions, it will be a good exercise. So find the equivalent operator for these two. A cap equal to dy dx plus x cap, dy dx minus x cap. A equal to dy dx minus x cap plus dy dx plus x cap. So try to find the equivalent operator for these. In the next lecture I will give you the solution. Until then, try it by yourself. So let's see some more things. So some A operator is given, that is d square by dx square, and we need to find the A dagger. So let's see, A dagger of this can be written as dy dx. Now this is something like A, B and dagger. So it will give you B dagger, A dagger. So it will be dy dx dagger, dy dx dagger. Now we already find it, this dy dx operator is skew Hermitian. From here, means A dagger will give you minus A. So dagger of dy dx will give you minus dy dx. And this will again give you minus dy dx. So this will be d square x by dx square. Minus minus will cancel out. So you can see that dagger of this A operator is giving you A again. So see, this is Hermitian operator, and the A dagger is equal to A for this. Now you can see for this also. Let's find for this A equal to I d square by dx square. So now find the A dagger. So take the A dagger, then dagger will give you minus I outside, and inside you will get d square by dx square. So dagger of d square by dx square again give you the same, but you have the minus outside because of this I. So A dagger will be minus A. So this operator is skew Hermitian. So you can solve the same way here. Just difference will be I will change to minus I, and that's how this result will change to minus A. Now for this d cube by dx cube, you can write it this way. It will be third term also. Now there will be 3 minus signs. This will give you minus d square by d cube by dx cube for this thing. So here A dagger will be minus A. So that's how you can check any operator, if that is skew Hermitian or the Hermitian. Now see, momentum operator, position operator, energy, Hamiltonian operator, energy, potential. So all these observables, I told you these all are Hermitian operators. So take the dagger of anyone, you will get the same value. Just like take the example of the momentum operator, that is minus I h cut divided by I h cut dy dx. So dagger of this will give you dagger of this, and this means complete this. So I will give you minus I, it will be I h cut dy dx dagger. So dy dx dagger will give you minus dy dx. So it will again transform to the minus I h cut dy dx. So that's how you will get P dagger equal to P. So try to solve this, you will get P dagger equal to P, and for all the position, Hermitian and the energy, you will get the same. Dagger will give you same value. So that's how you can say that all are Hermitian. Now let's take some complicated things. So if operator is given in this form, e to the power exponential power minus I pxa, and check for this operator if it is Hermitian or not. So A dagger will give you, means you know how to find the dagger of exponential term. It will applied on this power or the index. So minus I pxa, the dagger of this will give you minus I will change to plus I, and dagger of px a, and you know this px momentum is a Hermitian operator, so px dagger will give you px again. So this is equal to not a, and this is not a, so that's why we can't say that this is not Hermitian. We can say that this is not Hermitian. Let's see some more examples, interesting ones. So if operator A is given this I px x square plus x square px divided by 2, so find the A dagger for this. So A dagger will give you minus I, and these all momentum and position are Hermitian operator, so dagger will give you same value. So it is only changed by minus sign, that is A dagger will be minus A. But for this one, a dagger equal to I px x square minus x square px divided by 2, this will give you a dagger equal to a. So what is the difference between this and this? So when you try to solve this, means let's solve this and see what is the difference. So here we have this operator, apply the dagger, so it will be dagger of this complete, so this will give you minus I outside, so minus I by 2. Now dagger of this, so when you apply the dagger on this first component, it will give you dagger of AB dagger will give you B dagger A dagger, so this will come to the forward and this will go to the second side, so it will be x square px and this will change to px x square. Now see, if you take the minus common, then it will transform to this one, and this is same as this. Now you can write this complete one as a, means when you take the minus common, it will again change this minus to plus, and this is a again. So that's how this thing changed. When this was plus here, that won't change the sign, that's why we are getting a dagger minus a, but here this minus will change the sign and a dagger will be a. Now let's see one more interesting thing, or you will learn from here definitely. So if an operator is given in this form, I x square plus 1 dy dx plus ix, let's find the a dagger first. So dagger of this will give you minus I, and dy dx dagger will give you again minus dy dx, so that will change this minus again to plus, so it will be I dy dx x square plus 1 same, and this I change to minus I x square. So this will be your a dagger. Now see, you can't just compare these two, means you can't check if it is Hermitian or not, because that must be same as a if it need to be Hermitian. So you can't compare because this is in a different form. This dy dx is in here and x square plus 1 here, so you have just opposite ways, so you can't compare. So we must find the equivalent operator for this to compare with this. Okay, so let's try to find the equivalent operator for this, means because that is the second operator we can write same as this. So let's see the equivalent operator for this. So dy dx x square plus 1, I told you just apply this operator on the wave function psi x, that will give you your equivalent operator. So apply this on psi x, so dy dx of x square psi plus psi. Now this dy dx will apply on this, so it will be again product rule, x square d psi by dx, and then 2x psi plus d psi by dx. Now take this psi again outside, and you will get x square dy dx plus 2x plus dy dx psi. So this operator can be written in this form. This is the equivalent form of this. So let's write in place of this dy dx x square plus 1, write this thing. So it will be I x square dy dx plus 2x plus dy dx minus I x cap. Now see, this will be I will be multiplied inside, it will be I 2x, so 2x I cap minus 1 I x cap, it will give you 1 I x cap plus 1, and inside you can take this dy dx common, it will give you x square plus 1. So it will be x square plus 1 dy dx, because it is now in the right hand side. So you will get I x square plus 1 dy dx plus I x cap. And see, now you can compare this with this first one. It is the same as the a operator. So a dagger equal to a, so we can call this operator as Hermitian now. So that's how you can check, means whether when sometimes you don't get the same results and you can't compare, then you need to find the equivalent operator to compare this one. So see, if you are getting any time you are getting this x square of polynomial time on the right hand side of dy dx, then always find the equivalent operator in that form, means this polynomial should be on the left hand side of the operator dy dx. So always find that will be easy and the good solution. So let's see the completeness relation. What is the completeness relation? So if we know complete set of eigenstates of an operator A, so anyhow you find it the eigenstates, or you know the eigenstates of an operator. So I told you can write your any wave function or any cat in that eigenstates. Then any general cat can be written as, this is also cat, the wave function can be written in this form, ci c1 phi1 c2 phi2. That's how you can write. So we already discussed this thing. Now let's see what is the value of the ci. So see, let me tell you first thing, in the Euclidean space you can represent any vector in the these eigenvectors or the basis vectors, that is I, j and k. So this whatever the coefficient is there, that represent the projection of this original vector on that particular basis vector. Means this 1 represent that it is 1 in the I cap, 2 in the j cap, 3 in the k cap. So here the ci represent the projection of psi on the phi. Okay, so and how you find the projection? By the dot product. So a dot b cap or the a dot b gives projection of a on the b, you know that. So we can write ci as phi I psi. This is the inner product of phi and psi, that will give you ci. So I hope you understand this thing. How can we write this ci as this? This is just an inner product of phi and psi, and this is projection of psi on the phi. Now ci is this, substitute this value here. So you can write this wave function as phi I, and this is scalar now. Okay, this is some number, so you can write it here. And if it is some scalar, you can write it either right side or the left side. So let's take it here. So this will be here and this will be here. Now see this equation here. This psi should be equal to psi. So when it can be possible, because this is a vector, column vector, this is a column vector, and this is again a vector because this is a outer product, you can see. So see, this must be a identity matrix, only then this is possible. This psi should be psi. So we call this as identity operator. This is called the identity operator, this thing. Now, and this is also called the completeness relation. How we can call it that way? This is the sum of all the basis vector possible, and if you take this kind of product of all the basis vector of particular any space, then that will give you always the identity operator. So let's verify this. Let's say we have 2D space. So in 2D space, we know I and j, they are the basis vectors, and they can be written as 1 0 and 0 1. That's the column vectors. So only two vectors are possible. So this is the all possible vectors here, that is I and j, and we can represent them as phi 1 and phi 2. Now this, for the 1 phi 1 phi 1 and phi 2 phi 2, some of those will give you, they must give you this identity matrix. So let's see if they are giving or not. So this is this, and the second will be transpose of this. So it will be 1 0 and 1 0, 0 1 and 0 1. So this complete sum will be phi 1 phi 1 phi 2 phi 2. So this will be in the Euclidean space will be I and j. It will be 1 0 1 0, 0 1 1 0 1. Now if you solve this, again you will get 1 0 0 1, and this is the identity matrix. So this verifies the completeness theorem, okay, or the relation. Same if you have 3D space, then it will be I, j and k. Then you will take this sum for the three basis vectors. That will be 1 0 0, 0 1 0 and 0 0 1. And you apply the same relation, there will be one more term, that will be k, and that will give you 1 0 0, 0 1 0 and 0 0 1 matrix, and that is again the identity matrix. So see, this is a very important relation. For 3 it will give you this identity operator. For the 4 it will give you 4 terms, 4 into 4 terms. So that is the completeness theorem. Means if you know the complete set of eigen states or the eigen or the basis vectors, then you can write this. Means for all the basis vectors, this will always give you this identity operator. And there are many helpful results for this. So let's see the one of the result. I operator, that is identity operator, is very useful operator, as it can be inserted in any place at our convenience. Means with our convenience we can operate this anywhere. So let's see how we can do that. So we have this psi. This represents the probability, you know that. And let's see the help of this. Means we can just place this I operator here. It won't make any difference, because you get either apply here, you will get the same thing. So, and this operator can be written in this form. We already proved this. This is the completeness relation. Now take this with this and this with this. So it will be psi phi I and phi I psi. Now see, we already proved this, that this is the inner product and the projection of psi on the phi. We already proved that this is ci. So write here ci, and this is just a transpose. It will be ci conjugate. Now see, this is nothing but ci conjugate and ci. This will give you ci square, and this represents the probability. So because this is the probability, that's why this is representing probability. This is the proof that ci square will give you probability, because we started with the probability and we are getting this result. Now for the I, for all the basis vectors, this will provide the probability of particular wave function for the particular basis vector or the eigenvector. So it will be c1 square, c2 square, c3 square, and complete set if you know, so that will give you 1 always. So if psi is normalized, means psi must be normalized, only then this will be valid. Otherwise you need to divide with the normalized coefficient also. So we already discussed that. Now see what we are getting here. Means let's see what is projection operator. So we'll discuss these two operators, that is projection operator and unitary operator. So first is projection operator. So we discussed this is completeness theorem. This is equal to I. So let's call this is again a matrix. We know that this is a matrix because this is identity operator. So let's call it as this is a lambda I. Okay, call it some operator lambda I. Now let's see what this operator is and what is this operator giving us. So apply this operator on the wave function. So it will give us this, because we know this is equal to this. So you can just place in place of this. Now see, again this is the projection of psi on the phi. So this will give you Ci, and this is a scalar. You can write it either here or here. So it will be Ci phi I. Now see, this is equal to this. And what is the meaning of this? See, we already seen this, that this I, j and k represent the projection of R on the I, j and k. So this will be coefficients representing the projection of R on the I, j and k, means 1i, 2j and 3 on k. So same here we are applying this on the wave function, and we are getting Ci phi I in terms of the basis vectors, means it will be C1 phi 1, C2 phi 2. So what this operator doing? This operator giving us the projection on particular, means for it will lambda 1 will give you projection on the phi 1, lambda 2 will give you projection on the phi 2, and this C1 C2 represent the coefficients on that particular basis vector. So that's why we can say that this operator is nothing but projection operator, because this is giving us the projections on all the eigenstates or the basis vectors of this wave function. So same as here, for the R you can write in the Euclidean space x I cap, y j cap, z k cap, and this x y z are coefficient, means projections on I, j and k, and same relation we are getting here. So if you apply the I here on the R, so you will get xi, and that is because this is your projection vector, and that's how we prove that this is your projection vector, because this is nothing but IR will give you only the x value. This is the projection of R on the I, that is x, so it will be x converted in here also, so it will give you xi. So this represents the projection of R on the x axis. Same for j, you will get yj, and for k you will get k, and means k here, and z. Same here, you are getting the projection of psi on different basis vectors, and that represents the coefficients. So that is why we are calling this as projection operator. So I hope you now understand about the projection operator everything. So there are some points you must note about the projection operator. So the eigenvalues of projection operator are 0 and 1. So eigenvalues of projection operator will always be 0 and 1. The sum of two projection operator is a projection operator. So sum of two projection operator will be projection operator only if operators are anti-commute. So we will discuss about this anti-commute, commute and commute. First, only you just need to remember that if you need to prove the two operators as commute or the anti-commute, then you need to check that if sum of two projection operators is coming projection or not. So if it is coming, then you can call that anti-commute. And the product of two projection operator is a projection operator. Then it is possible only if operators are mutually commute. So just note down these points. We'll discuss about them. So no need to worry. And try to prove if you know already about the commute and anti-commute. Otherwise, I will discuss them in detail. So that's it for today. Thank you, everyone.